start lecture 19 for the course corrosion protection methods. And topic we are talking about materials aspect for corrosion protection. So, we have been discussing grain size effect as well as other factors which can have influence the corrosion rate depending other factors related to the surface microstructure or surface pattern. Now, if we consider only the grain size effect, no other factors associated with that, we have seen if the material shows active behavior all the time without achieving passivity, it can actually have a detrimental effect on the corrosion resistance if it becomes finer. Now, when we talk about active behavior and then talking that we are telling that it does not achieve passivity. So, there are two other aspects. The material can have spontaneous passivity or active passive behavior. So, let us consider two other factors. So, we are talking about grain size effect, and we are talking a kind of a general trend, as we have mentioned that there are many factors which would influence the corrosion behavior of a material. It is not only grain size, it also depends on the morphology, distribution, size of the second phase, and then the surface pattern, surface texture, as well as then the composition would come in, like even in a bulk composition can be same, but locally the composition can change due to the precipitation or due to the second phase formation. We will talk about that. Now, if we talk about grain size effect, we talked about the single phase. Now, multi-phase can also come in. Now, we are without indicating those multi-phase or single phase, we are just trying to understand the general trend in terms of polarization behavior. So, we have seen the polarization it can have three: active, it can have active passive, and then it can have spontaneously passive. Fine. And we are talking about environment. So, environment is also a factor. Now, in an environment when it shows active, fine grain, poor corrosion resistance. Now, a material can show active passive behavior in an environment. If we try to see the polarization plot, this is log of current density and this is potential. The plot could be like this. A typical active passive behavior. Why it is active? From E core, so this is basically E core, and corresponding if we draw Raffel slopes, then it shows I core. And that time in this particular situation, this is I core and this is cathodic process where this is activation controlled. Okay. And if we consider, and this is nothing but I critical, which is the maximum current density which needs to be crossed during polarization for that material in a particular environment, then only we can achieve passivity. So, up till this, that means the nose of that point, the maximum current density point, which is the I critical. So, let us say this is E critical. Till this point, this particular zone we can say active zone. Now, beyond that, so from this to this particular zone we can say unstable zone. And beyond this to this point, so we can say this to this point, this is nothing but passive zone, and beyond this transpassive zone. Depending on its position in a particular environment, it can be oxygen evolution line or it can be pitting initiation potential. So, what we are seeing that once we cross the active zone and cross I critical and going to beyond this potential range, and if we can stay within this range, we can get a very, very low corrosion rate. Why? Because this current corresponds to I passive, and we could see that this is actually less than I corrosion. I corrosion corresponds to the active zone. So, now in this such situation, if the material does not find an opportunity to go to that passive zone by self polarization or polarization by external current source or external power source, we would always stay at this point. So, that means this stay point is decided by if no further polarization to anodic side. Okay. So, this polarization can be this particular polarization towards this side. This polarization can happen, this one let me just put it there. It can happen due to local change in concentration, and the classic example we have seen titanium platinum alloy system, where the material initially would have a very high rate of dissolution corresponding to active I core, and then there could be a possibility of dealloying and then redeposition of platinum on top of titanium surface, and that platinum will take the potential of titanium in the passive zone, and we achieve passivity. And there the reason being the hydrogen evolution exchange current density on platinum surface is very high compared to that the same hydrogen evolution process on the titanium surface, and that is what potential is taken to that level. So, this is we can say the local change in composition and dragging the potential to the passive range. So, that way we can get to the passive range and we can have a very low corrosion current corresponding to I passive. So, there could be possibility of external DC power can take the potential towards the positive direction and it can get to passive zone. Still we will have a very good corrosion resistance once we achieve passivity. So, that is possible in case of, that is the very concept of anodic protection. We will talk about that. So, that means we are forcefully taking the potential towards the passive zone and we keep it there. So, these are in general two ways the material can get to that passive zone. But if we try to see the effect of grain size there, in general what has been noticed that if we make it finer, the change is not uniform on all those critical points. So, we might see that if it gets finer, the I critical would increase, I passive could decrease, as well as active corrosion rate could increase. So, this three situation can happen, fine. So, now if we try to compare the fine grained one with the coarse grain, so let me draw it again. All those zones are given here. So, let us say this is for coarse grain. Now, if we try to see the polarization behavior of the same material in fine grain zone, fine grain situation, the plot would have this kind of behavior. This typical behavior can be noticed. This is for fine grain. What we are observing? I critical is increasing, so I critical coarse grain is less than fine grain. What does it indicate? It indicates that in order to achieve passivity during anodic polarization, we need to go to a very high level of current density, because this point needs to be crossed before we could go to the passive zone. So, that means locally it can have a good amount of corrosion before it achieves passivity. So, that means passivity, attainment of passivity would be difficult. So, this situation, it indicates what it indicates? It indicates that difficult for fine grained material. Now, there is one more observation. If we try to see the active corrosion rate, how do we measure active corrosion rate? We measure this way, extension of taffel slopes, and here also we extend the taffel slopes, we get those points. So, in this case it is this and here it is this. So, now you could see that I core. So, if we in short we can say fine grain means Fg, coarse grain is Cg. Okay. This is for, so this is for coarse grain and this is for fine grain. So, this is our first observation, and the second observation is I core for fine grain active zone is very large compared to I core coarse grain active zone. It is similar to the behavior what we have discussed in the last lecture, where the material shows active behavior all the time, no passivity, fine grain would show higher corrosion rate than coarse grain. Now, at the same time we could see the passivity attainment would be difficult in case of fine grain, because I critical has gone up. Now, if these two conditions are not there, definitely the material would not go to the passive zone on its own, because it will stay there. Now, see this local change in concentration where we have seen in case of titanium platinum, this situation can also arise due to some other variations in the material. It may not be a local concentration change, but a local precipitation within the material, that is also possible. But here the local change happened due to dealloying in case of titanium and platinum, dealloying as well as redeposition of platinum. We can say or similar. So, this particular thing we can say or similar situation. So, that means there is change in the material and that would lead to an increase in potential in that environment and it can attain passivity. So, now if these two things are not there, so definitely it will stay in the active zone and active dissolution of fine grain would happen at a much higher rate. So, now we could see two aspects, that means active dissolution for fine grain is much higher than the coarse grain, similar to the active material, and at the same time this material shows active passive behavior. So, that means it is going through active zone and reaching to passive zone and then transpassive. So, that case the passivity attainment is also difficult. Now, one more situation we have come across. If we consider the passive current, so this particular current density I passive for fine grain and this is nothing but I passive coarse grain. If it reaches to the passive zone due to polarization, then the third observation is I passive, if we in short if we write P. So, I passive for fine grain is much lower than I passive coarse grain. So, now we could see that three options possible, but the third option actually gives us an idea that the material can have a very high corrosion resistance in case of active passive material if we go to a finer grain, but at the same time if we can achieve passivity. So, once we achieve passivity, so that means if we have this condition, then corrosion resistance improves. So, two condition, fine grained, and the second one is reaching passive state. So, now this is with respect to active passive. So, there is one more option which is for spontaneous passive material. So, if the polarization is spontaneous passivity, so in case of spontaneous passivity, we get a plot like this. Okay. A typical plot pattern looks like this, and this is achieved if we go back to our earlier lecture series. So, this is my anodic polarization line, and if we see the cathodic polarization where it cuts, depending on that we can have whether it shows active passive or spontaneous passive. So, if the cathodic line cuts here, okay, so that case we will see. So, this is my cathodic line, and cathodic polarization. So, now it is cutting here. If we try to do polarization, and the machine potential stat will give me the plot like this. So, like this plot we would see. So, the plot pattern would be like this. So, this is active passive, similar to what we have seen just before discussing spontaneous passivity. Now, if the line cuts here, okay, so this is my cathodic polarization line. Now, that time my polarization plot will be So, in case of active passive, in case of spontaneous passivity, the plot is like this. The green line, if you observe, it will be like this. So, that case, if we consider this is for coarse grain, now if we have fine grain, actually the entire line shifts to the left. So, let me just draw this line here. So, the entire line shifts to the left. In fact, this material is actually showing corrosion rate corresponding to I passive. So, this is my I passive for coarse grain, and this is fine grain. Okay. And that time passive current is here. Okay. As well as now you could see that the graph is going towards left, and in fact, if we consider active passive as well as spontaneously passive, both cases you see the passive current density here, it goes from here to there, and here also it is going here to there. So, that means both cases fine grain, and if we try to compare these two current densities, I passive fine grain is much lower than I passive coarse grain. Okay. So, that means again the corrosion resistance improves. For what? Two condition again, fine grain, at the same time it should show spontaneous passivity. So, now if we try to understand why fine grain material shows a very strong passivity, for that let us see what are the extra thing with fine grain material. So, if it is fine grain, grain number or grain density, see grain number per unit area, if we mention that way, grain density goes up, area goes up, and here we are seeing passivity. Whether it is a spontaneous passivity or active passive situation, if it shows passivity, that means passive film is formed. Passive film formation, and that passive film formation relates to the activity of the surface. Higher the activity, better would be the passive film formation, because the reaction area is increasing. Now, grain boundary, and at the same time if it is fine grain, the grain boundary region active zone, that is also increasing. So, the reactivity of the material is enhanced in that environment. Hence, it would also help in achieving strong passive film. So, we could see one after another these events will happen, and then it will lead to increased corrosion rate for the material with finer grains, showing active passive or spontaneous passive behavior in an environment. But remember, situation can change if we change the surface condition, if it is strained surface or with surface with no strain, or environment change in environment, that could also lead to change in the material's response. But this kind of situation, what we have discussed, that active behavior, active passive and spontaneous passive, can achieve in general in case of materials, but situation can be different. Remember this again and again, I am emphasizing that part, that active experimentation in lab is very important to get an idea about the grain size effect on the material's corrosion response. So, let me stop here. We will continue our discussion on corrosion protection if we consider the materials aspect in the next class. Thank you.